Object detection papers. Today we shall be looking at this paper, Unsupervised Anomaly Detection with Generative Adversarial Network to Guide Marker Discovery. Now, for some time now, you see that we have been looking at some anomaly detection papers, and in sequence to that is this other one. What you see here is number one, it says it's unsupervised. The unsupervised means that we don't have labels for our training data. And they have made use of generative adversarial network, which is essentially a two network, the generator and the discriminator. And what they are trying to work on is on some medical images, and so this to guide them in marker discovery. So yeah, essentially the work in this paper is they perform an unsupervised learning to identify anomalies in imaging data, so as candidate for another pipeline. Now, what's interesting about this work is the training data contains only uh, images, samples, training data that don't have any anomalies, and that is intuitive of what you would expect, because most time in real life scenario applications we are often encountered with the the data point that are normal. It's occasionally that we see abnormal data point, and we cannot predict the abnormal data point, but we know for sure the normal data point. Let me say that, rephrase that. We can't predict the variabilities of abnormal data point, but we can for sure have a fixed set of the normal data point, because we know what is normal. We're used to what is normal, whether in the production environment, whether in uh, high diseases or brain diseases, brain tumors, or whether in skin cancer, or whether in whatever disease, whatever abnormalities you might think of. It has applications in various domains. So we always know what is normal, but what is not normal, we don't know all the possibilities. We might have just seen a few. There might be novel diseases that we have not even seen at all, that we have not experienced. There may be novel anomaly that we have not even experienced before. And we want our system to be able to take care of even the unseen ones. And that is really the power behind machine learning, artificial intelligence, and deep learning. Being able to generalize to unseen data. So here they call their system AnoGAN, which is a deep convolutional generative adversarial network, and they used to learn a manifold of normal anatomical variability. So accompanying a novel anomaly scoring based on the mapping from the image space to a latent space. So they use the deep convolutional neural network for that. Um, yeah. So here they demonstrate that relevant anomalies can be identified by unsupervised learning on large-scale imaging data. So this is their framework. Now here is the input image, and they did some little pre-processing on the input image, and they sent those input image into a training uh, to train the generative adversarial network, which is a deep convolutional generative adversarial network. One important point here is that they use healthy data, that is data that does not have anomalies in the training phase. After training, fine-tuning, and they learn some parameters, some weight, and that essentially is our model. Now the model is ready. Now during test time, which is during the inferencing, they now have unseen data that have not uh, been trained with, that was not shown during the training. So this unseen data could actually be anomalous or normal point. So they want to now identify anomalies in this uh, image. Now this one happens to be an image that has anomalies. So the model that was trained here is now used to uh, do inferencing on this unseen data, and this is the output. It was able to generate anomalies. The anomalies are the ones that are in red. So the pre-processing step includes extraction and flattening of the retina area, patch extraction, and intensity normalization. So they did some pre-processing on the eye data, the image data. So, and they now use generative adversary training on the LD data, and they perform testing on both the unseen LD cases and unseen anomalous data. Okay, so now they use GAN. Let's go on. So now this is using GAN to learn the representation to identify anomalies data. So here is the deep convolutional generative adversary network. We're going to look at this paper in subsequent tutorials, so stay tuned for that. So it's essentially as the generator, it passes in a latent vector, that's a noise z, which is just a set of random numbers, and the generator learns to generate a realistic image. Then we feed in the output of the generator and the real image into the discriminator. The discriminator learns to differentiate and classify real as real and fake as fake. So here they did a t-SNEEZ visualization of this this particular uh, of uh, of an anomalous data. So they did a, because after you have learned, you have trained your model, your DC GAN, now you can now use that model to do inferencing, and during inferencing they extracted the last layer, as you can see here on the feature representation of the last convolutional layer in the discriminator. So they extracted this last layer and they use a t-SNEEZ visualization to visualize what does the image, the anomalous image, look like in this last layer. And they discover that okay, you have white, some blue, and some red, and the blue represent the normal point while the red represent the abnormal point. You can see that it's clearly demarcate where the anomalies is and where the normal point are. There's a clear demarcation there. Okay, so these are details of the unsupervised manifold learning of the normal anatomical variability. We will come back to some of these in the next walkthrough. This is the loss function, the value function for the two-player minimax game, because that is what essentially the generative adversary network is. Okay, so mapping new images to a latent space. We'll come back to this to get the details, but essentially you are having a generator is taking a noise Z. So from latent space representation Z, and is trying to transform Z into X, such that X will be the realistic normal images X. Okay, so we'll come back and look at the details walkthrough of what is happening here. This is a residual loss. We'll have a tutorial on the residual loss soon, but essentially it measures the visual dissimilarity between the query image and that is generated in the image space. So this is the generator, this is the query image, then you measure how far apart is what is generated from what is supplied. Like I said, we still look at this in more details. These are interesting. So we also have the discrimination loss. That's the discrimination loss. Something interesting we'll still look at in details, so stay tuned for that. And we have an overall loss which gives us the discriminator loss and the residual loss with some parameters fighting it. So this is essentially what we do differentiation on. Okay, so now during the detection of the anomaly, so you have a new query image X, and we pass it to our model. So we'll still come back to the detail of this. So they carried out experiment on the clinical high resolution SDOCT volumes of retina with 49 B scans. So and total volume resolution of 49. So this is the data set they used to carry out the experiment, and they did evaluation and they reported some metrics compared to other existing method. We'll come back and look at these implementation details in next walkthrough. So this is what you have here in this figure. You will see in this figure we have the pixel level identification of anomalies on exemplary images. Let's quickly go to their result, then we'll come back to they use Python 2.7 and TensorFlow library, and they use Titan X graphics on CUDA. Let's look at the results, and so this is their result. This is the result that they have. This table shows the result. So these are other methods, but this is their method, and you could see that they have the highest precision. They have a slightly lower recall, slightly lower sensitivity compared to this one, but they have a high specificity, and clearly they have the highest area under ROC curve. Okay, so that's it for now. We will come back to some of the more technical details of this in later walkthrough as part B of this paper. So thank you very much for listening. I hope you benefited something from this, and do give us a like, and please consider subscribing. Thank you, and see you in the next one.